The Fourier transform is a powerful idea used across engineering, physics, computer science, audio processing, and image analysis. Its central purpose is to break down complicated signals into simpler building blocks, waves of different frequencies. Imagine listening to music. A song contains many sounds happening at the same time: drums, bass, vocals, and guitar. While the sound appears complicated, your ear and brain separate components, allowing you to hear the bass drum distinct from the singer. The Fourier transform mathematically separates a complex signal into its basic frequency parts. Any signal can be represented as a combination of simple waves. These simple waves differ in frequency, which is how fast the wave repeats, amplitude, how strong the wave is, and phase, where the wave begins. Think of it as breaking down music into individual notes, turning something complicated into something structured. Many real-world signals are easier to understand in terms of frequency. For example, a faulty engine makes noise with unusual vibration frequencies. A crack in a metal pipe changes its natural frequency. Blurry photos can be improved by adjusting frequencies that create textures. A human voice can be compressed by keeping only important frequency components. Analyzing frequencies often reveals patterns invisible in time-based representations. Imagine a smoothie blended so well you can't see the ingredients. It's impossible to know what fruit was used just by looking. The Fourier transform acts like a filter, separating the smoothie into strawberries, bananas, and mangoes. Once separated, contents are easier to analyze. A complex signal becomes clearer when separated into its frequency parts. The Fourier transform is everywhere, often behind the scenes. In audio and music, it removes background noise, recognizes music tracks, and compresses audio files. For wireless communication, cell phones, Wi-Fi, and radio signals use Fourier-based methods to encode and decode, allowing efficient sharing of frequency space. In image and video processing, it compresses images into formats like JPEG, sharpens blurry images, and enables edge detection. Medical imaging devices like MRI and CT scanners rely on Fourier techniques to convert wave patterns into 3D internal images. In engineering and physics, it analyzes vibrations in buildings and machinery and helps understand wave patterns in oceans, earthquakes, and galaxies. When we look at a signal in time, we see how it changes moment to moment. The Fourier transform converts it to frequency, showing repeating patterns. Time domain asks, what is happening now? Frequency domain asks, what repeating patterns make up the signal? It's like hearing each instrument in an orchestra one at a time. A single pure tone on a piano has one frequency. A chord, however, has multiple tones, creating a more complex sound. The Fourier transform tells you which notes are present, how loud each note is, and how they combine. This applies to radio waves, light waves, heartbeats, and speech. Engineers value the Fourier transform because it turns complicated behavior into something organized and measurable. By breaking a system into frequency parts, you can filter out unwanted noise, strengthen important signals, detect hidden patterns, and predict system responses. It reveals structure inside complexity. The Fourier transform breaks complex signals into simpler wave components. It allows us to understand and modify signals by shifting our perspective from time to frequency. This shift makes patterns clearer, systems easier to design, and information easier to store, transmit, compress, and clean up. The Fourier transform is the essential tool to reveal hidden frequency structures.